Yeah, I can start directly.
Sorry about that. The next speaker is Damiano Mazza, who is going to speak about the categorical approach to descriptive complexity theory.
Yes, thank you, Samuel. Okay, so yeah, I'm gonna start right away because we're already more than 10 minutes late.
Don't worry.
So first, very brief introduction to what is descriptive complexity, because maybe not everyone in this room knows about that. So first of all, just plain standard complexity. We all know the definition of decision problem, which is extremely, I guess, disappointing mathematically. It's just a subset of the set of strings. Okay, there's really nothing too fancy about it. And then the theory, of computational complexity attempts to classify these things. Okay. According to how hard it is to decide them, okay, by means of typically Turing machines, okay. So understanding how many resources, okay, are needed to decide, okay, something like this, okay. And of course, a Turing machine can decide something like this because Turing machines accept, words, binary strings as input. So, you give it a string, you see if it accepts or rejects. And you can count, how many steps it took, how much space it needed in terms of, the work tape that he used. So you can define all this. Okay, and you get this very I don't know, deep theory of trying to understand, how hard problems are. So descriptive complexity takes a very interesting standpoint that says that instead of just considering strings, okay, you should think that anything that you can give as input to a computer program is a finite structure in the sense of first order logic. Okay, and so in particular, if you want to talk about strings, you should consider a theory, okay, a logical theory, okay, that has a binary relation symbol that you axiomatize as a total order, okay, and then a unary predicate that has no axioms whatsoever, okay. And now if you consider the models of this theory, okay, strings, well, modulo isomorphism, modulo renaming, the elements of your, the finite model, okay. Modulo renaming the elements of your finite set. These are exactly binary strings, okay. If you maybe don't see why, let's make a little picture. Wow, I can't. Very much. Okay. So you have your finite total order, which is something like this. Okay. And then so this is the symbol. This symbol gives you this. Okay. And then the other, remember, there's this predicate is 1, which has no axioms whatsoever. So it's just a subset of the points. Okay. So for example, here I selected these ones. Okay. And these are interpreted as the strings 1, 0, 1, 1, 0. Okay. So the total order gives me the positions available in the string, and this predicate gives me which position is 1 and which is 0. Okay. And again, of course, to get exactly strings, we have to reason modulo isomorphism because I could name the positions in with different names, and that's perfectly equivalent. Right. So instead of talking about just strings like that, okay, descriptive complexity talks about finite models of this theory. Okay. And so decision problems become subsets of the finite models of this theory. Okay. And this allows us to change our standpoint and say that actually what complexity tries to do is to classify problems according to not how hard it is to decide them, but to describe them, okay, in terms of a logical language. Okay. And I'm going to give you immediately an example here. So consider this is a very basic example that everybody uses. the set of palindrome strings. Okay, it's a subset of this. This formula here, okay, is true exactly for palindrome strings. So you see, what does this formula say? So in this, so we have taken this language here, okay? So in particular, you see we have the symbol is 1, okay? And then we have allowed ourselves, this is what it means, logical language. I mean, we have allowed ourselves to add some, some power, to the basic logic that's in the theory. Okay, in particular, we have added these two relation symbols, okay, unary predicate and a ternary relation symbol, that we axiomatize, so they are interpreted, this one as the maximum of the chain, okay, in finite models, and this one as the graph, as the truncated graph of addition. Okay, so since we have a finite model, and it's a total order, we can assume that it's in bijection with 0, 1, 2, 3, okay, etc. So we have addition on them, okay, and this one is precisely addition. Okay, so now you see that this formula it's telling you if for every pair of positions in the string, okay, which when you add them together they give the maximum, okay, that means that basically I am looking at two positions that are symmetric with respect to the center, okay. Well, I ask that either they're both 0 or they're both 1, okay. So that's how you describe palindromes like this. Okay. So you see, in particular, I use the formula that's it's very simple. It's first order, and in fact, it's universal. It doesn't even use existential quantification. Blah blah blah. Okay. So I can start to think of problems in terms of what logical symbols I need. Okay. What logical power I need to describe the problem instead of how many resources, how much time and space I need. Okay. So this is descriptive complexity. Yes.
Why do you use relations instead of functions?
Because since we're interested in finite models, it's kind of awkward to use function symbols because typically, for example, if your model has only 2, okay, it's only 0, 1. What's 1 plus 1? And it's better like this because this you can just truncate it, and there is just no symbol here that will have 1, 1 and something here. Okay, it's better. It's more convenient. Okay. Yeah, but then in reality we will see that we can use well, it doesn't matter. Yeah, I mean, it doesn't matter. Okay, so that was descriptive complexity. So we've seen that it uses finite models, okay, and and logic. So now, since we're at SYCO, we need to talk about categories at some point. So we're going to now take a look at all these things from a categorical perspective, in particular from the perspective of categorical logic. Okay. So I'm going to introduce right away the categories that are the basis of what I do. I call them Boolean categories, okay, but their full names should be Boolean extensive categories, okay. And here's an equivalent, I mean, a definition that's equivalent to the one, the Boolean extensive means that it's an extensive category such that the poset of subobjects of every object is a Boolean algebra. Okay, this is the definition, but it's equivalent to this. So it's a category with just finite products, finite coproducts, and such that this is the coproduct of the terminal object. Okay, 2 copies of the terminal object. So this has 2 special properties. It's disjoint, it's pullback space stable, and it's the subobject classifier. Okay, so categories like this are called Boolean, and you have the natural morphisms between them are functors preserving these 2 structures here. Okay, finite products and finite coproducts. In particular, they also preserve finite limits because, in fact, all this implies that your category has finite limits. I mean, it is extensive. Yes?
Get the pullback stability just from knowing that the subobjects are Boolean algebra?
You get pullback stability from knowing that this is pullback stable. Okay, you have to ask that 1 plus 1.
You said that it's equivalent to say that the subobject posets are Boolean algebra.
Yes. This is equivalent. Yeah, all these conditions here are equivalent to saying. Yes, absolutely. Yes. Okay. Now, a few examples. One that is very important is I mean, I'm only looking. Sorry, yeah, no. This probably it's interesting. So this you can see this as a progressive weakening, okay, of categories of structures that are standard in categorical logic. So Boolean toposes, okay, those are the biggest, structure. I mean, the most, the ones with the most structure, categories, the most structures, and then you can weaken them to Boolean pretoposes, okay, and this is a further weakening, okay, that we're considering, okay. So Boolean extensive category is the full name, but I'm just going to call them Boolean categories, okay. I'm just going to omit extensive because it's quicker. When you speak of toposes, usually you think of large categories. Here we're going to be interested in small Boolean categories. So, for example, the category of finite sets is a very important example of Boolean category, but we take just the skeleton, okay, so that it's small. And another Boolean category that is not a topos is the skeleton of countable sets, okay, and functions. And then there's a bunch of syntactic categories that we will see now. I introduced this because it's in relationship with logic. Okay, and this is the relationship with logic. Okay, you can present Boolean categories by means of logical theories. Okay, so it's what I'm going to call Boolean theory. Okay, Boolean theory is a triple of a set of sorts, a set of relation symbols. Okay, each with a certain arity and a type. Okay, and a set of axioms. Okay. Here I'm restricting to finite, okay, Boolean theories. So all these three things are finite, but in general they could be infinite, okay. And the thing that I ask is that there's something that I'm not gonna. The definition is a little bit more complicated when you have to say exactly what the axioms are, but I'm gonna gloss over that. But just think of them as universally quantified axioms that contain no existential quantifiers. Okay, only very special existential quantifiers. Okay, that are provably unique. Okay, in a sense that I'm not gonna detail. And then okay, from this, okay, the relationship with Boolean categories is that each theory like this, okay, induces a Boolean category. Okay, the syntactic category of that theory, which is morally the category of sets and functions definable in that theory. Okay. For example, the category of finite sets is the syntactic category of the empty theory. Okay, when you have just nothing at all, no sorts, no relation, nothing. Another very trivial example is the category, the syntactic category of the inconsistent theory, which is just the one object and one morphism category. And then another example here, for example, this is the theory of graphs. Okay, you have a set, a sort, okay, which represents the set of nodes of the graph, and a binary relation symbol, okay, which represents the edges, the set of edges. And so the syntactic category of this, you have to imagine it as something that has this object n, okay, and then you can do all products, coproducts. You have a bunch of other objects here in this category, okay, and then you have one special sub-object of this one, and then you can build everything out of this. For example, that you can do in quantified free logic, basically. So, for example, you're going to have another sub-object of this, which is the complement, okay, of E, okay, and I don't know, everything that you can do in I don't know. You're going to have a set, for example, a subset of this, which we can call, for example, with this formula here, because you have equality, okay. Let's call it like this. So this is the, or if you want to, you can add this. So this is the set. No, sorry, what am I doing? Sorry, I didn't mean to write this. XX, sorry. So this is the subset, okay, of all morally, okay, of all nodes of the graph which have a loop around them, okay. So this category allows you to basically to speak generically, okay, of a graph, okay. And so on. An example of a Boolean category which is not of finite presentation is the one, the F omega that I defined before, right? The skeleton of countable sets. So now we define this category here. Okay, Boolean category is finite presentation. So it's the category of Boolean category of finite presentations and logical functors between them, but modulo isomorphism. So that this is actually a one category, not a two category. Okay, because naturally it would be a two category. Okay, but you quotient everything. You take the quotient under natural isomorphism so that it becomes a category. And so in particular, skeleton of finite sets is the initial object of this category, okay? And this category is small too, okay? It's a small category because, of course, finite presentation is, there is only a set of finite presentations, okay? How am I doing with time? Oh, wow. All right, and now I get to so I guess if I do this, I'm already happy. I can stop after this. Now we'll see the link, okay, with complexity, okay? So that's already enough, what I said, to do basically all of, I mean, most of, the typical complexity classes that people are interested in below NP, okay? So define this category here that I'm gonna call the category of data specifications as just the opposite of the category of Boolean categories of finite presentation. And this category is very nice. It's extensive, okay, meaning it has all finite limits and finite coproducts which interact well with those finite colimits. And in particular, extensive categories, you should think of them really as categories of somehow of spaces of some sort. Okay, their objects behave with respect to finite limits and colimits, and coproducts exactly as we would expect spaces to behave. And so you can really see this as a category of spaces. And the objects of that category, of course, they are the Boolean categories, small Boolean categories, finite presentation. But to mark the fact that I'm considering them in the opposite, I'm just going to write spec of the category. And we have a functor that I'm going to call the global section functor, okay, from data to set, okay, that just takes a data specification, so something like this, okay, and returns the set of its points, meaning the set of morphisms from spec of f. Remember, f is the initial object of this category, and therefore it becomes the terminal object here. So it's just a set of points, okay, the set of maps from the terminal object to spec of B. And by the usual things of, the main point, I guess, of categorical logic, you can recover models as functors. Okay, so the global section functor in fact maps a spec of a category which is presented by theory T to the set of finite models of T. Okay, because this, maybe you don't know, maybe let's write it. I think most of you know it, but maybe some of you don't. So a logical functor like this, okay, is exactly the same thing as a model. A finite model, sorry, because this is finite, okay, of T. Okay, this is the crucial thing of categorical logic. So models become functors, okay, and due to Lovier, from a long time ago. So since in data everything is read backwards, okay, so this becomes spec of f, okay, terminal object into spec of f of T, okay. So a map like this, remember, I'm considering them modulo isomorphism, okay? Yeah? Because this is a model, but I want models modulo isomorphisms, okay? In order, so for example, a map from spec of f to spec of f of, remember that theory string, okay? This is exactly a binary string, okay? It's just nothing but a binary string, and okay, so now I can speak of binary strings in my, do I want to read the rest? Yeah, I guess. Yeah, I guess actually, no, let's first do this. So now I have strings, okay, I have maps. And what I can do is that, so now consider a morphism in data, okay, above spec of f of string, okay? And now take this spec of f. So remember, this is just a binary string, okay? Now I can ask myself the question, does there exist, a map from here to here, okay, such that this factors through this. Okay, can I lift this map here? Okay, and so the strings that can be lifted, okay, they define a subset, okay, of strings. Okay, so each map like this defines a problem. Okay, in the sense, remember, so each f induces a subset of 0, 1 star. Okay, is it clear? Right. Okay. It's just the set of strings that are lifted through this. Okay, and you can in fact you can see them as the image of the image via the global section functor of f. Okay, so this is a map like that. When you use the global section functor, you bring it to set, so it just becomes a function. Okay, you take the set theoretic image. Okay, and it's a subset of the image of this, but the image of this, remember, it's the finite models of this, which is just strings. Okay, and now, so I can ask, what sets, what problems am I defining with morphisms like this? Okay, and it's very simple, in fact, to prove this theorem, that you're defining exactly the recursively enumerable sets. Okay, so this category data somehow knows about computability. Okay, it's just implicitly knows that the only things that it can do are recursively enumerable things. Okay, and then you can go further. Okay, and you can define classes of morphisms. Okay, still like this. Okay, morphisms like this, but you restrict. Okay, how they are. Okay, you don't consider all of them, and you can characterize complexity classes in this way. Okay, you get NP, you get P, you get non-deterministic log space. You even get a deterministic log space. I didn't write it, but you can do that too. And then other things, I guess that I haven't still explored everything, but it's most things that you do with descriptive complexity you can do here. So I guess I'm going to skip directly to yes.
Machine or recursive functions?
Where are they? Yes. Okay. Yes, that's a very good question. So how do you prove this theorem? Okay, in fact, it's really not hard at all. Okay. So first, already this here gives you the proof that all these sets are recursively enumerable. Okay, because you see there's an existential here. Okay, and everything here is finite. Okay, this is just, you see this arrow here. Okay. This is a finite presentation. Okay, so this x here is going to be of the form spec of f of something, okay, of some theory t. Okay, so this map here is just a finite model of t. Okay, so you see, in order to prove membership of x to the set, that the f is defining, I just have to exhibit this witness, okay, which is a finite model of t. Okay, and then you just have to check that this thing is true, but you can, of course, this is computable. Okay, all these things are perfectly computable. Everything is finite. Okay, these maps here are very easily computable. Okay, these f's here via the global section functor, they define functions from the set of finite models of t to strings. Okay, and these functions are always computable. In fact, they are very, very much computable. They're like less than log space computable. They are super easily computable. Okay, and so so computing this composition is very easy. So if I give you the witness, you can check whether x is in this or not. Okay, sorry, no, only if it is. If it's not, you don't know. Sorry, what? No, yeah. In fact, this gives you just the. I was saying, yeah. This drawing already gives you one inclusion. Okay, the other one, I'm not sure I really want to draw that because no, I'm not going to draw it. But it's you encode Turing machines as Boolean theories. So basically, what you do, actually, I guess, let me draw it, and then I stop. So you have your thing here, spec of f of the string. So what you do is that you have a Turing machine M, okay, and you define an extension of this theory here. Let's call it Tm of M, okay. So it's a Boolean theory, okay, that is an extension of string. So it contains the models of this theory here are exactly so. Spec of f, something like this, okay, is exactly a pair let's call it U, of a string, okay, which is the string that's going to be thrown away by this morphism. So this morphism here maps this pair XU to just X, okay? It's just a projection, okay? And these pairs, so what's U, okay? U is the theory is made in such a way that U is a witness of the fact that the machine accepts X, okay? It's just basically, it's if you want to, so you add, remember string is a logical theory with just one sort, right? So you add two sorts here. You have a sort S and a sort T for space and time, okay? And so this gives you basically so say that this is T and this is S. The model will be a sort of table, okay, of the space-time of the Turing machine with input X, okay? And you can check, by, just by local, checking of just, very simple axioms that this is in fact, the space-time of the execution of the machine, okay, through the, okay, with that input. Okay? And so, so this gives you completeness. And in fact, then you can, the NP and P theorems are obtained by noticing that if this machine, this can be done for non-deterministic machines too. Okay, it's very easy, and it's actually the same thing basically. And then if your non-deterministic machine terminates in polynomial time, then you can instantiate this S and T, the space and the time, with polynomials in the length of the string, okay? But Boolean categories, they have polynomials. Remember, they have products and finite coproducts. So you already have polynomials. So you don't need extra sorts. And so that gives you, in fact, I didn't say it, but see, the propositional morphisms are defined by restricting to extensions here, which do not add any sort, as I did here, but only add relation symbols and axioms, okay? And so, so this will be a propositional morphism because S and T can be instantiated, and you don't need extra sorts. And for, P and L, you just, I don't know, you use actually the deterministic version works for P, and for an L it's more complicated, but okay. So I think I stop here because otherwise, yeah, it's already been, yeah. Thank you.
So I have questions. So, Mark,
yeah.
Do you understand how, for example, this result for NP say relates to the theorem that it's like the descriptive complexity theorem that it's existential second order logic?
Yes. It's simple to. In fact, basically adding relation symbols here, because you see you cannot add any sort. You can only add relation symbols. Is basically doing a second order existential quantification.
Okay.
That's basically what that's doing. Okay. And in fact, those other two characterizations, you see them. I call them horn crop because they really use the same ingredients, the same ideas. In fact, what I like about this is that really it's you get everything that you do in descriptive complexity. You get it here. You can redo it, and it doesn't cost more. It's just a different language. Okay, you can just formulate things in a different language, and hopefully you can do more. Okay, I had a couple of slides later to show you that you can do more things, but yeah, for the moment, another time. Yes.
I was a little bit confused by the separation you make between Boolean toposes and your Boolean categories. Because, and correct me if I'm wrong, but if you've got all finite limits on a sub-object classifier, you're basically at an elementary topos.
No, because you don't have powers. You don't have exactly. Yeah. Yeah. Okay. You know. Yeah, topos. Yeah, in fact, look. I mean, it's very simple. So this is the basic. I mean, this, you know what this is. It's here. Then basically you go from here to here by adding the fact that your category is regular, that it has images. Okay, so you add images, and then here you have to add Cartesian closure. You have the fact that you have exponentials. Okay, and this is why you're losing higher order from going from here, and you're losing first order from going to here. It's yeah.
One perhaps is the idea that if you just allow each object to have a power object that implies Cartesian closeness, but only assume for the terminal object to have a
Mm,
power
mm.
object. So
Yeah, in some sense, yeah, I guess. Does the terminal object have a power object? I mean,
yeah,
I mean, it always does because one.
So to be a subject classifier, that's
Yeah,
exactly
that means, yeah, okay, I see, yeah,
terminal.
sure.
It's the power object of the terminal.
Yeah, okay.
Okay. Is there any other quick question? If not, I suppose we should thank you again. Thank you very much. And I think that's it for